I do have an about me slide. I sometimes skip it. This time I have one. And I guess you see the screen right now, the presentation, right? So that's me. That's how you can contact me either on LinkedIn or go to my website. I'm there on the other social media platforms, maybe Twitter, but Discord of CPP India is the best place to get me also. And so we we are working on a system on a high performance telecom system where we had this need to gather a lot of data from a huge set, and that's where we actually had to apply lots of expressions, and we wanted to make them static and not runtime polymorphic in order to reduce the cost because it's a high performance system. Okay, as you saw in the title flyer of the session, C++ doesn't allow a struct to be a member of itself, a type to be a member of itself, because C++ needs to know the size of the object, and it's very it's not optional. So if you infinitely recurse by adding something to itself, it becomes a bit of a problem. So we have had this discussion with some of my friends where talking about JSON parsing, we have a recursion need, and the tree could go any levels deep. How can we represent this statically? Is today's quest. Okay, and I'm inspired by Ben Dean. He recently, on 30th April, just 10 days ago approximately, he gave this talk at CPP. Sorry, he gave the talk at pure virtual C++, and he worked on a system where he needs messages being handled and some expression or some logic filtering checks applied. And he had a very good presentation of how he could use Boolean implication logic in order to determine what the matching criteria were, how to reduce them and simplify them. And it's an interesting talk. It's a short one for half an hour. I'll request you to definitely go and watch it. This is the talk which when I watched, I was not decided about today's session, and this is what pushed me over the line on this topic. So we are doing something very similar, and I'll go through the parts where things are a little different, and I'll lead you to this talk when the parts are matching or the ideas are common. Okay. You've heard about me. I'm working on high performance scalable products, and I've done some open source enhancements. My other interests are CI, DevOps, lean automation, and with that, you can think of, uh, you know, uh, I love problem solving and optimization. So I'd love to have a team which goes faster with time, and I guess that's where. This picture is from a talk I gave on an invited event at a company's annual event. And I love doing conferences and solving problems. So if you have an interesting uh, a problem for me, just let me know. I'd love to talk. Okay, so in this talk, we are going to talk about expressions. They are everywhere of different sorts, but this is not what we are talking about. We are going to talk about in this talk about evaluating expressions for huge data sets. We work with millions, and it's called as big data. So for a reason. So we have expressions, how to represent the expressions, how to evaluate them. Something about simplification and optimization. Some of these parts I'll delegate to Ben Dean's talk. So I thank him a lot for his talk, just coming in time. Okay, so expressions are everywhere. We see these kind of things. Expressions are either a fixed constant kind of a thing, or they can be linear, quadratic, or very, very complex like the one at the bottom. Uh, I came across this simple problem video, which is about 3n plus 1. It was a very interesting video to watch where if you are an odd number, you would have to, there is a series that you have to calculate starting with a number. And if it's an odd number, you have to do 3n plus 1. If it's an even number, you do half of divided by 2. And so, all these numbers, whichever number you start, the theory is that, as we know, all numbers finally come down to this loop of 4 to 1, 4 to 1, 4 to 1. Okay, it was a very interesting one. Talking about expressions, I was reminded about this one. So what are the kind of expressions that we have in our programming context? We have something like this, and you have different kind of things like initialization expressions. You have const expr expressions. You have some mathematical operations going on. You have functions being called, some functions being performed. Some things are constant. So expressions are everywhere, and we can come across a lot of them. So what exactly, how do we define them? It's a combination of constants, variables, functions, and operators. Okay, they follow some rules of precedence and association, and they finally produce a value. In our case, the one problem that I'm talking about, it is going to produce a set of data based on the criteria that you are giving. So anyway, we'll see that during the thing. So let's take a typical start with a database example, which everybody knows about. So is the following an expression? Hell yes, right? You are getting from the table, there's an operation happening, but there is a clear expression in the where clause. It oops okay, yeah. It has many combinations and ors and some value checks and all sorts of things. Looks like a very good company if you have joined before 2014 or your job level is above 10. But look at the last line. If the job level is below 5 and work from home percentage is above 80, I love that. So all these employees will be found, and I'm sure they would be given a raise. So expressions in networking, we know that there are routers which follow rules, which allow traffic or route traffic to some other place. This is what a typical configuration looks like. You can't see the exact expression, but as you see here, your port is specified and IP address is specified, and it is followed by the router. When you try to capture a packet, you might specify something like this. Host is this IP and port is 80 or 8080. When you're working with a captured PCAP, you want to go very deep into protocol things like SIP is being discussed here. So if the SIP message is going to info@cppindia.co.in and the content type is JSON, you want to work on those records, right? It's very normal to do that. Web search, is that an expression? Yes, our all too familiar web search are also expressions. So if you say, let's look at the first expression here. I'll just get my laser out. So you want restaurants at this location which have this type and they are open at the current moment. So all these are expressions which the search engine has to go back and evaluate. Okay, and then go to Lakshadweep, not Mauritius. Uh, Shopping are also expressions. You want to specify a price range or some rating or a brand or how new the product is or how much discount. So all these are just expressions. So we need to see how we can deal with these expressions. Okay. Now take our typical database example. We have this query from the previous slides itself. So what do we see here? Like we discussed, the where clause is an expression, and I've just highlighted the expressions in that statement. So you have the date of joining being checked, or job level being checked, or whether the guy has done some initiative, one of many, or there is a combination situation with the bracket and an and operator in between. Okay, so let's represent these. We are now talking only about the where, so I've removed all the other aspects of the thing, and I'm just rearranging them in a different order. So the operators are pulled up as nodes which aggregate the condition values. Okay, I'm just representing the same thing in a tree fashion. Okay, because we know expressions tend to be trees. So you see the first two clauses were odd, so you can just OR them. And then the third one was odd also with the result of the first two. Let's say we are working only with binary, but it doesn't have to be binary. Like you'll see in my implementation, it's not binary. And then finally an OR has to happen between the result of this and an expression and expression which was in the last line, which had exactly these two things. Okay, so you need to do some logical operators uh, and match some conditions. Okay, let's do some creepy crawlies and organize it in a way which we are little familiar with. Just it's just rearranged into straighter lines, right? So now we have levels of expressions being evaluated. Okay, so this OR, which is a combination of these two, is going to work at the same level with this one, and it is going to yeah, okay, this and is going to be at the level of this result. So I should have pulled it up, and finally you get the result. Okay, so the depth is not the same, but basically you have a tree. Okay, now this is the expression representation. What do we see here? We see that there are some fields and values specified by the user. Okay, we also see that there are many of these operators specified, and we need some sort of matching between all of these. Okay, so this is what it looks like. You have some fields and values and what to do with them, whether it is less than or equal to. So you have to apply a matcher. Uh, and then for all the summing up the results, uh, as you see in the definition, an expression evaluation gives you a final result, right? So we have to finally get the result. In our case, a data set. So you get some data set because of the first clause, and then you do an OR, and then you do an and then finally you get the final data set. Okay, now let's start the solutioning based on this thing. Any questions so far on the tree?
Uh, uh, Ankur, I actually do
Yes,
have a question.
yes, please.
Ankur, the sorry, I really missed the starting 5 minutes of the conversation, and I think my question could go wrong from there. But we are not expecting SIMD operations while optimizing this expression tree, right? Or are we gonna come to SIMD operations as well?
Not in my talk, not in my talk, because uh, what we were dealing with was
Why
would not
I think
fit, would not fit in a
I
SIMD or
might have missed a little in the starting because I'm somewhere, maybe
yeah,
that's why. Because
yeah.
uh hmm,
So I'm not looking at the data set of actually doing the search. How that
hmm,
happens, I think we better delegate to, uh, I mean, we have, big data databases,
hmm,
so it is
hmm,
delegated there. But what we have to do in process is something based on the results that we have thereafter. Okay, so
hmm,
so yes, evaluation could definitely use SIMD. You have to. So this is what relational tables would do very well. They would have an index, and index is a very small value which you could do SIMD on, and then you search the indices on in the various clauses for various conditions, and then you shortlist the data, and then you finally fetch the data which you really want
hmm.
to return in a typical database implementation. Okay. Okay. The box in the center is showing an in. It's a special kind of matching. We'll touch upon this, but not in quite detail. Okay, it's just a fancy way of saying many ORs. Okay. Okay. So solutioning uh, would my recommendation would be to create strong value types and extraction. Okay. So let's extract the values from somewhere where we want to match it. Okay. So basically from the data set. Okay, so let's create so based on the clauses that we just saw, the conditions that we saw in the previous diagram, I've just created the possibilities of a joining data type and an initiative, let's say enum. We can have a job level, which holds an int value, and a work from home percentage, which is also an int value. Okay, so the question is, but why do we need these? Like, don't we have the ints? They already work. So the The reason is why I'm recommending this is you can actually have the comparisons of these specified. This is one minor reason, okay? One of the smaller reasons. So you can actually have a custom operator or a way to compare, which might not be exactly what the int or a basic data type does. And when it comes to some combination field, it will definitely be more complex than this. So I'm not assuming that you just have basic data types or something. Okay. One of the bigger reasons is actually to do with how the value is supposed to be extracted from the record. The record is an employee record. I'm representing it as a struct here. Okay. A relational table would have it this way. But a blob, the NoSQL databases of the day, they don't have something like this. So it is a much difficult job to extract that field out of the whole blob, which is not very well formatted. Okay. So, but I'm making it simple for our discussion's sake. It's a struct employee, which has exactly those four fields which we want. Okay. And in order to get the fields from this, what we can do is implement a get function. Okay, this would get from the employee. This is the function which knows where this field is present. Okay, so if it sees a type T, it knows based on the type T that it has to return some field of the employee. Okay, but in case of, as we see as is underlined here, the job level and work from home percentage both are ints. So if you ask the employee for an int, like you ask a tuple for an int back, but and if there are more than one, which one is to be returned? How to disambiguate? This is where the strong types will actually play a part. They actually behave like a tag value, and they actually would help you rather than passing int. If you passed a job level, you would only get back the job level. Okay. You can have get functions in the employee, but you have to explicitly name that function. It cannot be a generic code if you have to write get job level in one line. In the next line, you have to write get percentage. In the next line, you have to get initiatives. It's not scalable. It cannot work generically. Okay. So we are building a generic thing. Yes, Persh, please.
Uh, Yeah, Ankur, I wanted to ask, like in the right hand side of the example, as we have templatized the employee category for the solution of a problem, can't we use concepts from C++20? Like
Yes.
where we can define the like we can define the constraint of the variable of a type name as a concept which could
Yeah.
be employee type only,
Yes,
so
it is
that
possible. In this case, I wonder if it is really helpful because as I show you next slides, we might not know what fields are present in the employee or
sure, sure,
I
sure.
think because by doing this, you give a customization point. I'll cover all this. So let's go through the flow. I
Yeah,
think we'll
yeah,
get to
sure,
that.
sure, sure, sure,
I
sure, sure.
think. Okay.
Yep, yep.
Then you can ask me the question. So let's see that, sometimes an employee or a
Yeah.
record can have many dates like we have on the screen here: joining date, leaving date, promotion date, birth date, anniversary. It could be like IP headers have two IPs. UDP headers have two ports. It's very common to have many fields of the same data type. So there again, you have to disambiguate. So how do you refer to one or all of them? You also, apart from T, you can actually specify an occurrence. This makes it very programmatic. By changing an int, you can go through all the fields or something. Okay. So the default get should actually just not compile. It would just static assert and saying that the field is not supported. So how do you actually support it? By actually specializing for your type the get function. Okay, so as we see here, we have two gets here. Both are working with time points. They get time from the employee, but one is getting the joining date and the other one is getting the uh, exit date of the employee. And the only thing which is different is 0 and 1. This, in the context of the employee, is clear to the employee record as to what it is in order to be able to provide this kind of an overload. Okay. So it's very convenient to do that. And you can by default say if you just have mostly just one fields for most of the types, like not every field is repeated, then you can just have this default to always work with the zero occurrence, and maybe the implementation, the specialization of that one is going to you know going to just work with the one field which is present. Okay, okay, I think I need to go to the next slide. That last point has stayed as a matter of reformatting the slides. So allowing the customization point of get allows implementations to have their own access. For example, employee can definitely, go at the default field. But what about something which is not even a well-defined data type? Like we work with packets in networking, they are just sequence of bytes. There isn't a structure there to pick things. So here the data which you're extracting the field from is also templatized as data. And I continue to call it employee just for you to connect the dots. It's now not an employee, but just some type which you want to use. And now you can get from it an IP address. For example, it is an IP header. Okay, and it is just a span of bytes. And you want to get the IP address from it. So you create an IP, you copy the bytes into a value, which is an IP, and you return them. Okay, I could reinterpret cast. If you are tempted to reinterpret cast in place inside the span, you have to be very sure that you are obeying the alignment rules. It would complexify the slides. Plus, one very good tip here is when you're working with some offsets inside a buffer, please define the IP header. I have it defined somewhere as a proper struct as per the RFCs. And I'm saying that pick the offset of this field inside this struct. Okay, so it gives you an offset, which is what you go and read. So this actually documents what you're trying to do instead of putting magic numbers or adding new constants which say the same thing, and just increase the scope of you going wrong. So use the offset of this thing. So you can actually read it. You go to the offset of source IP in the IP header and copy the size of IP over to your field. Okay. Okay, so this is the value extraction, and the customization points help you actually do non-default, non-trivial stuff. Okay, now how do you represent the field which is given in the expression? Okay, so we just said that the employee has some fields. Now we are seeing what the expression has. The expression has a field which is an expectation from the employee record. Let's say the field expects a type at a certain occurrence. So this is what it means when you say date of joining. It means the field of type time point with an occurrence of 0. If you want to see date of exit of the employee, it is the same type of time point, but the occurrence is 1. Just what we saw in the previous slide. So this is a basic representation of the field. There is a value type and there is an occurrence, and it actually holds the value, which is the value you want to match with. Let's look at how the clauses would translate into. So on parsing the expressions, we want the DOJ condition to turn like this. Okay, a field of joining date. I'm not specifying the occurrence, so there's just one of them, but you could actually say comma 0. Oh, sorry, I made a strong type for joining date, so I don't have to specify. There's just one joining date. But if I had set date here, then it would need, in case of many date fields, it would need an occurrence. So we have the job levels to match the job levels. Again, job level 10 and 5. And work from home percentage is also parsed into its own data type. The strong data types help you create the field. Now, why do we need the field? So this is the same field value which is coming from the other one. Okay, just a point about the list value. The list value specifies one of many fields. It's just a fancy way of saying or. I think I mentioned that before. And so it could boil down to either many of these conditions separated individually, or you could merge them into a list value kind of a lookup. So it could be a slightly different data type than the field that we showed there, but it's just one of the many possibilities. Okay. All right. So same to same. How does the matching actually work? So we represented the clauses as fields. Okay, this is the field, and it would match some rows in the let's say in the data set. Let's say you have the other one field, which matches the job level greater than 10 or something. We have oops, okay, a duplicate slide. So we have the other condition of job level 5, it will match some other records, and we have finally the work from home fields which would match some slides. What do we want is actually make sure all of this data is picked up, because that's what forms the result of your expression. Okay, so now how to pick this data, how do you mark these selections? Okay, let's look at that. We have the fields. Okay, this is replicated from the other slide. It is just the field. It has the value type and the occurrence and the actual value to be matched. Now, when you want to match, it provides a facility called as apply. Okay, this apply can take a callable and pass its value to the callable. Invoke the callable with its own value that it expects to find. So this is a very good way of having a lot of possibilities of what you can do with the value. Any questions at this point? Okay, I'll proceed. So this apply can apply, on the field, and the value is the expected value. So what can we do with this? So let's say for the job level field, you have a type def, a using declaration. So job level field, work from home field, and the same kind of things, just renamed for ease. So you have the job level field which expects 10. And what you can do, let's pass a printing lambda to it so that it prints the output. This will print the 10 value inside the job level field. Okay, so this is what you expect to find in the matching records. Okay, so this is the expectation of the expression of this clause of the expression. So actual matching can happen too, like you passed the print lambda in the previous screen. Now, how about passing a matching lambda, which you can customize? So this is where you will see the field data types, the field, uh, using declaration of value type, the field value type, and the n come in play, and the matcher is going to match an equal, and it will specify these things from the from the object, and uh, use on the captured employee. So when you traverse through employees, you will make sure that you process them one by one. It is implied check, and because the only thing that the field can pass is its own value, the expected value. So you capture the other things and you make sure that you get from the employee the value type, and you match it actually with this. Okay, I've assumed, no, not assumed, I've said that this is equal. So this is how you can now apply equal, and what will be returned? The bool return of this would be to actually match or not match, whether an employee even matched or did not match. Okay. And the matching part, I will refer you back to the talk by Ben. He also has a very similar kind of a matchup where you see a field and value are there, and the value matches, a dynamic get of that field from the message. So he's working with messages like I told you before. So you get from the message this field and you check that the value matches. Okay, so this is a simple matcher like equals, which I showed, but you can get fancy with less than, greater than, less than, equal to, and all those things. So Ben's there and done that. So I'll refer you back to that half an hour kind of a talk. It's a nice, very, very, very good talk. Okay, so now you can have all sorts of matches. Like we saw the equals, you can do all sorts of matching. So that will help you match records. Now, based on your domain types, if the number of records are of a fixed number of types, like you have for JSON, like you can have some string types, number types, object types, array types, and Boolean types. In our world, we also had a fixed number of criteria that we supported. If that is the case, that's a clear winner to actually work with static types. If you just don't know the types, you will have to resort to things, intrusive things like inheritance, and you'll have to create with a base classes of, let's say, you can make expression based class and then work with that throughout. So, but then that brings in the reference semantics, and the virtual call at the end is the one that could be prohibitive for you. You should measure and check. If it gives you the simplification, that's great. If you want the open types being to be possible, then you go for it. But if you have the fixed number of things that you support to be looked up, for example, when you do an employee search on a web page, uh, or fixed things that you support, then you can just use then you can just use variant. I'm coming to that in the next slide. Okay, so if we know the types upfront, what we do is use variant. So we say an expression field is an expression of either the job level or work from home percentage or joining date. Okay, any of these three can be passed as conditions. Okay, so with that, what does that lead us to? Now we are in a position to define the expression tree, because what we want, what we have is the fixed number of types that we have. Okay, we still need to see that we can go arbitrary levels, which I'll show you right now. Okay, so let's say you have a lot of sub expression types. Okay, and so your value type actually becomes a variant of all those sub expression types, and you can have the value type in a vector. Okay, and I put the logical operator here, I guess. That's optional. It's a design choice. So value type here can refer to expr itself, because the template can refer to itself, and it is allowed to be evaluated at a later time. So since template evaluations happen late, the template gives you the possibility of having a child of itself. So a naive approach which one would do is, you have let's say you don't have the expression here, and you have the sub expression types creating one expression. So one of possible types. So you can have a variant of sub expressions, and now that becomes a concrete type of an expression with, let's say, three possibilities. Now, what is the next level of it? The next level of it would be the expression with three possibilities also can occur in the next level. Not only that, but this expression, which is already having three possibilities, is also a child of that. So if you manually expanded the expressions, uh, by hand, you would actually only limit yourself to the number of depth that you can go. But if you let the template instantiation do it, this could instantiate on the need basis. Okay, so all we need is a expression. Yes, Parsh.
अंकुर, I just wanted to ask, जैसे जो आपने सॉरी जैसे अभी हमारा एक्सप्रेशन ट्री है जो टेम्पलेटाइज्ड है, ठीक है, तो माय क्वेश्चन इज लाइक, इज इट फॉर लाइक ये कंपाइल टाइम में ही सारे जितने भी हमें सब टाइप्स चाहिए विद द एक्सप्रेशन एंड द सब एक्सप्रेशन टाइप्स, ये पहले ही ऑप्टिमाइज करके जो इररेलेवेंट वाले होंगे, लाइक यू सेड देयर इज वन एक्सप्रेशन एंड देन थ्री सब एक्सप्रेशंस, एंड unnecessary, मतलब like we just need one, two and three, not one, two, three. So जो ये compile time optimizations में ही सारे निकल जाएंगे ना हमारे, right?
Yes, I have not made these const expert, but Ben shows how you can actually use const expert also in these kind of things. So yes, some of these can be evaluated, can be eliminated if you know them. In our world, that was we were not working with constant expressions. We didn't know what my users would want to use. It's like writing an SQL, actually doing the SQL processing. So you don't know what conditions the user can give. There are fixed set of conditions. So we have the sub expression types fixed, but we couldn't say what the final expression would be. So that would be formed based on the user's inputs, and it would actually instantiate the the depth to any arbitrary
Mhm.
levels.
Also, Ankur, I wanted to ask like this endeavor to RDBMS via
Yeah.
like in a programmatic C++ approach. Like, is this benchmarked, and do we have numbers that this pushes the you know what
Yeah.
I'm asking here?
Yeah. So the toy repo that I'm referring to here for this
Okay.
talk is not benchmark, but we have some performance numbers for our product, which is dealing with
Mm-hmm.
not databases, but we are dealing with networks and packets. So
Hope so,
I'm just
sir.
conveying the idea here. So, but I don't have numbers, but I think it's very important to see. What we didn't do is to compare it with something. Uh,
Mm-hmm.
you would have to implement the inheritance um, side of it and the static polymorphic side of it, and then compare. I think that's what you have in mind.
Yeah. But like
Yeah. So
obviously,
yeah,
since as you said, it's a toy repository for now, and
yeah,
more about the idea of
yeah.
creating
But it
the
is, yeah,
database.
it is. So I'm telling you the concepts which we learned at work. I'm not able to
Hmm.
share with you my code from the product, but this is like that. So yes, the performance has been measured, but no, it has not been compared with an alternate approach. We did work on things and some improvements, but we don't have the static to runtime difference.
Sure, Uncle. Thank you.
And
Uh,
the benefit here comes from knowing how many types you have. So if the variant is always having those three, four types, which
indeed.
was a very small number for us, something like that.
As you said,
So
as you said in JSON, we already have a limited set of types, so
yeah,
we are already fixed, and वो compile time में सारा easily sort हो सकता है, rather than when it comes to complex projects like games where objects get a little too frisky to handle,
yeah.
because games
But
has a lot of uh-huh.
yeah, yeah, yeah. Please
I was
complete.
just saying, like, I was just saying that games, in its the gaming engines and games have a lot of types that they produce. They are not very single validic
Yeah, yeah,
type of thing. That's it.
yeah. You should
So
see
in
the
the,
compilation errors that we came across while working on this. Yeah.
I'll
Uh,
sure will.
it was unfortunate that we could not use C++ 20 for our things. So
So this is
it
running.
was
This is all C++17.
yes, yes, easily
Oh,
C++ 17. Yes.
अच्छा तभी
I
concepts
think
नहीं use हुआ तभी
I think
concepts नहीं use.
no, yeah. So it is because I was doing it in a second time, and so I wanted to come to concepts, but I could not. A bit of
Mm-hmm.
a lack of time thing here, but I wanted to play with concepts here because saying a concept here might simplify the variant further, I guess.
Yeah. But anyway,
Okay. Yeah.
Uncle, let's continue. Yes.
Okay. So how do you evaluate the tree? Before that, just take a warm-up example of printing the tree. Okay. So since I had the operator noted in the expression, so I'm also printing the operator here, and you have the sub expression. So they are variants. So you cannot just work with them. You have to visit them. So for every sub expression that is there in the sub expression vector, we just visit them and output them onto uh, cout. Okay. And this was I mean, it became so easy to deal with things that um, it would also get into the multiple levels. I'll show you in the next slide. I don't think I show that here. Uh, but you get the idea. So every sub expression is itself an expression, and it just recurses into the possibility. So at the top level, you go through the first node and all its children, and every child goes through its child, and every child goes through its child, and you can actually see the entire tree in the output. Okay, so now just like you can traverse and print the tree, how about actually fetching the record? So let's say we have something like a fetch based on the expression. So, and the outcome is the set of data finally that you want to return. This is what the expression gives you. So we, based on the operator that we have in the expression, which I maintained, we create the operator. Now this operator can be or and uh, it doesn't come in the play till the data sets are there. So anyway, so you just instantiate that operator and you transform all the sub expressions, and in order to put it into the resultant set, okay, what? Now you visit the expressions by fetching the value which is there inside the expression. Now, if the expression was a sub expression, it would just go inside the fetch and recurse into it. So recursion has really helped us a lot in order to do the same thing again, same thing again, same thing again in the next level, like I was saying in the previous slide also. And you come back, roll back up with the data sets that you have got. And how do you roll back up? You have to apply the operator that you have. So let's say your tree has 3 children. You go to the first one, get a data set. Go to the second one, get a data set. Remember the colored rows which I showed previously. You go to the third one, you get a data set. Now you have to combine them based on the operator that you have. And the operators are just a specification on the initial conditions which the user has given, but on the data set, they become set operations finally in order to come to the final set. So, okay, so just one more time, you have an operator on the various sets that your children will give you at every level. So the root of the expression is also a level, and all it does is check its children, and works with applies the operator on the set, on the many sets that you get, and finally you get one set out. Okay, so what does that level do? It goes through its children, and creates a set of set, and the entire tree is in a way replicated back into a tree of sets. Let me show it to you, in terms of a little pictorially. Okay, so this is the same slide. Pardon my animation has also repeated, but this is the same slide from before. This is exactly the expression that we have been working on in this talk. These are the field values, there are matches, and there are OR operators applied. Now, if you fetch the data at every level, now you have the field value have now changed to data set. Did you notice that? The field value are now a data set. So every condition gave you a set of records from your database. Okay, then you have the operators, and now the operators have to work on the data sets. So they become, or becomes union, and becomes intersection. So each of the ORs is going to union the data sets that its children give, and the data set of and will be an intersection of uh, of the child data set. And finally, you keep on applying level after level, and you can make sure that your final data set is ready. Okay. Now I wanted to get into union and intersection, but you can imagine union is just bringing together the two sets. Let's say if there are two vectors, you would merge them into one. If it's an intersection, then you have a set intersection done on the two vectors. And so only those items is in the result of an AND, which are present in both of those conditions, right? That's exactly what the AND should do. So only those records are fetched which are there which meet both the child condition. Okay. And this is also an OR, by the way, but yeah. So do we think we have evaluated it and finally we have a set by doing a union or intersection, and finally a data set has been got for the query which the user has given? Okay, makes sense. Okay, finally, this is how the tree was represented. The initial expression was split. I also got an advice from somebody on using RPN, which is reverse Polish notation. It is a different way of representing the expressions. You could transform this into that kind, and it seems that it is easier to parse the expressions in that format. But to convert the user's expression into that format, I had to do some study, which we never did, and we have a custom implementation of our expressions. There are many parsing libraries like Lexi and Boost, and a few others which I'm forgetting right now, which can help you parse things out of expressions. Okay, so what we saw today was how you could have recursive types even at static uh, polymorphism time, and you know, and eliminate the runtime polymorphism overheads, but please measure, right? Uh, if it's a style thing, then it's a different thing. But if you want to really compare, then you have you should actually measure and then decide. Recursive structure is possible thanks to templates and lazy evaluation of the templates on instantiation. Okay, matchers can help optimize the matching, reduce operations, and short circuit decisions. So we didn't have time to go there. I've delegated you to, I've requested you to go through, please, Ben's talk, and maybe we can discuss about this part later, if it suits you, if you're interested. Expression trees enable easy operations, reducing them to just traversal. All we did to get the data was to traverse. To print the data was to traverse. To even optimize, you would traverse and compare. Is less than 10. If you have two clauses, less than 10, less than 20, it is implied that less than 20 need not be evaluated. You could do these kind of optimizations. See Ben's talk. And it just becomes traversals. The ors and ands becomes union and intersections, and the set theory can help you work with sets. We had some conditions where the user put a condition such that the data set would be infinite, would need a full table traversal. So we wanted to detect that early, and we were able to do that using set theory, but that's for another day. And there we have it. Recursive structures for expressions and their evaluation. It's just a traversal. Thank you.